Okay, welcome back, everyone. We are still working with chapter 18, and in this video, we're going to talk about how temperature affects the spontaneity of reactions. So let's go ahead and get going. So, with this form of the Gibbs free energy, this delta G equals delta H minus T delta S. In this form, and knowing the sign that in order for a reaction to be spontaneous, delta G has to be negative. And so with this form of the equation, we can predict how all different sorts of reactions if they will be spontaneous or not at different temperatures. And we can do this by thinking about the sign of these parameters and what we have to do to make delta G negative. Okay, so let's just start working through some examples. So if we have delta H is less than 0 and delta S is greater than 0, so it is an exothermic reaction and the entropy of the system increases. We have a negative delta H minus a positive value, which means that this is a negative with another negative, which means that delta G is always going to be negative. And so, in this condition, the reaction will be spontaneous at all temperatures. Okay, so we're gonna go through the same reasoning for other conditions. Okay, so what if we have an endothermic reaction whose entropy decreases? So that means that delta H is positive and delta S is negative. And so this means that this T minus delta S term is a positive term because we have a negative times a negative makes a positive. And so a positive and a positive term means that delta G is always going to be positive in this condition, which means that a reaction under these conditions will be non-spontaneous at all temperatures. Okay, so now let's keep marching through the different options, the different possibilities. So another possibility is that we have an endothermic reaction with a positive delta S. And so this means that delta H is positive and delta S is positive. And so in order for delta G to be negative, this term, this T delta S term, has to be bigger than, has to be bigger than the delta H term. Okay, we can think of this with numbers. If delta H is 200 and T times delta S is 100, then delta G is going to be equal to 100, which is a positive value and not spontaneous. But if we increase the temperature, keeping this delta S term is going to stay constant. We increase the temperature so that now we have 200 minus 300. Now our delta G equals negative 100. It's negative, and so it is spontaneous. So this means that our temperature has to be large enough to make our T delta S term bigger than delta H. Now, something to know is that delta S is usually a small value. And so in order to make this T delta S term bigger than delta H, we need to go to high temperatures. Okay, so let's do the last possible combination. If the reaction is exothermic and the entropy decreases, then we have a situation where our T delta S term is a positive value. And so we have a negative and a positive, which means that this T delta S term has to be less than the delta H value. Okay, so we can think about this with numbers again. If delta H is 200 and T delta S is, if T delta S is a negative 100, then that means that we have 300. Hold on. I see my problem. So this needs to be a negative 100 because we said that delta H is a negative value. And so what we get is a negative 100, and we have a negative value, and so things are spontaneous. But if we get a temperature that is too large, because that's the only thing that we can change, where now this T delta S is a negative 300 value, now that entropy term has become large enough that it overpowers the negative of the delta H, and we get a positive value for delta G, and the reaction is not spontaneous. And so in this case, these reactions will generally be spontaneous at low temperatures. Basically, we've got to keep the enthalpy big enough so that it overpowers the entropy. So what we really are seeing in these conditions is that reactions can be controlled by the enthalpy, or they can be controlled by the entropy, neither or both. And so what do I mean by controlled? So we're really thinking about which of these terms is allowing the delta G to be negative. And so if we have where our delta H is negative, which is the favorable, and our entropy is positive, which is favorable, this condition is both enthalpy and entropy driven. Whereas if we have a positive delta H, that is going in the wrong direction for spontaneity, and a negative delta S is also going in the wrong direction for spontaneity, and so this is neither entropy or enthalpy driven. Okay, likewise, here our enthalpy is not supporting spontaneity. Our entropy is supporting spontaneity, and so this condition is entropy driven. And then here, our negative delta H is supporting spontaneity. our negative delta S is not supporting spontaneity, and so this case is enthalpy driven. So really what we have going on is that the entropy and the enthalpy are two things that help these reactions proceed. And they can compete against each other. And so you can have reactions that we talked about, like what we talked about at the beginning of this unit. We can have reactions that are not favorable with their energy, but they are favored with their entropy, and so they occur, and they can be spontaneous. One of these reactions, so the temperature at which a reaction becomes spontaneous is known as the crossover temperature. And that is where delta G is equal to 0. Or really, this is the temperature that you can think of for that at which the reaction switches from being spontaneous to not spontaneous, or vice versa. And so what we do is we set this equation equal to 0, we rearrange, and so the crossover temperature is the delta H divided by the delta S. We remember the crossover temperature is delta H divided. And so at 298 Kelvin, here's an example. At 298 Kelvin, the reduction of copper oxide to copper is non-spontaneous. Delta G is a positive 8.9 kilojoules. At what temperature will the reaction become spontaneous? And it gives me the values of delta H and delta S. And so delta S, and so the temperature that we're looking for is going to be delta H divided by delta S. And so we have 58.1 kilojoules divided by 165 joules per Kelvin. And this gives us a crossover temperature of units. This is in kilojoules, this is in joules. And so I have on the top is actually 5.81 times 10 to the 4th joules divided by 165 joules per Kelvin. So now I can type this into my calculator and get a number that makes sense. And I get a temperature of 352 Kelvin. And if I turn that to Celsius, that is 78 sig figs 79.0 degrees Celsius. And so that means that in order for this reaction to be spontaneous, I have to heat it up to about 79 degrees, 80 degrees. And once I hit that temperature or above, this reaction is spontaneous. Okay, I hope this makes some sense. We've got just a few more videos of this chapter, and I'm going to try to, in these next several videos, I guess about 3 videos, I'm going to try to pull all of these concepts together and give you a big picture understanding, as well as talk about how we do this stuff in the lab.